recently at Stanford. He's an excellent example of this more recent trend of linguists who take computer science seriously and contribute a lot to the community. Many of you are aware of the most influential works while a graduate student is the building up of the Stanford dependencies, which is now a core representation in a lot of NLP work, as well as a lot of other very nice lexical semantic projects, including one we're going to hear about today.
Thank you. Thank you very much for the invitation. Can you hear me? It's a pleasure to be here. And today I'm going to talk a bit about Gradable Adjectives. That was part of my thesis. And so since, I recently graduated, probably some of you remember, but when you're writing your thesis, at the end you're a bit tired of it. But then I decided to kind of revisit Gradable Adjective, and so this is why the title. So let me just give you a high-level picture of what I try to do in my thesis and still try to do now. So my research goal is really to build computational models that capture what people take away from language. And what do we take away? Much more than only the literal meaning of the string. So when we hear something, we actually infer a lot. So not everything is said explicitly, but we rather, infer a lot from context. And we do this all the time. And what I wanted to do is to try to do this automatically. And so what's our best contender so far? So probably Siri, maybe now, OK, Google. But so if you looked back at the Apple website a year ago, that was what you would see. Siri, it understands what you say. Talk to Siri as you would to a person. Say something like, tell my wife I'm running late. Remind me to call the vet. Any good burger joints around here? Siri does what you say, finds the information you need, then answers you. It's like you are having a conversation with your iPhone. So actually, if you now look at the Apple website, they removed that last line. So you don't really have a conversation with your iPhone anymore. But you still have this. It knows what you mean. And so their example here is, again, this any good burger joint around here. Siri will reply, I found a number of burger restaurants near you. Then you can say, how about tacos? And you are going to get a list of Mexican restaurants. And so what Siri is giving the illusion that it can make the following distinction, the distinction between what is said and what is meant. So like the literal meaning, if I have a string like I'm in the mood for Italian food, the literal meaning there is just, the string, I'm in the mood for Italian food. But what you mean when you say something like that, it's actually that you want to eat Italian food. And when we have conversation, this is exactly, the meaning that you get. And can we do this automatically? So when the, Siri came out, Stephen Colbert used it in his one of his shows. And so he started his show saying like, oh, I spend the whole day talking, with my phone, and now I have nothing ready. And so he asked Siri, write the show. And then, of course, poor Siri cannot understand that this is not really like totally fair. What would you like to search for? And so then Stephen Colbert, tries again, and at some point he gets really annoyed. And so he said to Siri, for the love of God, the cameras are on, give me something. What's Siri's reply? What kind of place are you looking for? Churches, camera store. So of course, Siri is totally unable to do the context-dependent inference that's required here for understanding what Stephen Colbert was asking for. And it's just backing off to, a bag-of-word model. And I guess God triggers churches and cameras triggers camera stores. So of course, I'm not going to show you that I can do this, right? Otherwise, I could start my own company, I guess, and we'll start much more locally and trying to understand under specification in dialogue. And this is something that does happen in dialogue. So when you have indirect, when you have yes/no question, sometimes you do answer indirectly and not explicitly with a yes or a no. But can we kind of understand the underlying response there? So that was actually the example on the Apple website that we looked at. Any good burger joint around here? Then Siri replies, I found a number of burger restaurants near you, which you understand as yes, they are, and it's giving you the list. But there is no explicit yes to that yes/no question there. And it continues, how about tacos? And then again, it could say like, yes, they are, you can go and eat tacos, and it's giving you the list of a Mexican restaurant. So actually, indirectly answering to yes/no question is something that's pervasive in language. And Hockey et al. In '97 had that studies that roughly a fourth of yes/no question are answered indirectly. If you have something like, will it rain tomorrow, and you get the weather forecast is cloudy in the morning, does it mean yes, it's going to rain, or no? And how are you interpreting this? Can we do this automatically? And what I did focus on is looking at scalar modifiers. So when you have a question like, was the movie good? Hysterical, we laughed so hard. How do you interpret this? Does it mean yes, the movie was good, or no, the movie was not good? So also, I will briefly mention other type of dialogue that I looked at, but I didn't find that many. But when you have like a numerical answers in the reply. Are your kids little? I have a 10-year-old or a 7-year-old. Do you take this as me having little kids or not? And so those gradable adjectives, they are inherently vague. And so there is a substantial amount of gray area between the clear instance here, little as the babies, and the clear non-instance adults. And then in between, it's not clear whether it should be a yes or no. So what I wanted to do is focus on scalar modifier and try to learn the scale of expression that's necessary to be able to kind of interpret those indirect answers to yes/no question. So can we learn the scale in order to determine how the answer is resolving the issue raised by the question? And those are quite interesting because they are inherently vague and highly context dependent. So one of the things is really like to never forget that there is a lot of uncertainty that's inherent in language. So some of the answers are going to be totally straightforward. Like the first one, was it a good movie? It was a great movie. I guess that everybody in the room here will agree that then yes, the movie was good. It was even better than good. That's what you understand when you hear this. It was excellent. But the other one, I don't know. Do you like my new haircut? It's interesting. What is meant here? Yes or no? And actually, I just recently did a study with Judith Tannhauser and semanticists at OSU on the role of prosody on scalar implicature and how, the so-called uncertainty contour can, help getting more scalar implicature. The kind of, was your date hot? It was good looking. Depending on how you utter that sentence, you can get more people to think it means good looking but not hot. And of course, this is like, I think, totally something that NLP is not able to handle yet. But we have to start somewhere and gradually, get to another point. So what are we going to try to do? We are going to try to infer the polarity, so yes/no, of indirect answers to yes/no question involving scalar modifiers. And so why it's quite important in conversational implicature for generation and interpretation of language. And how are we going to do that? Look if we can leverage, all the web data that we have access to nowadays. So what I started to do is to try to look for dialogue of the form I was interested in. So where you have a question and an answer both containing scalar modifiers as well as example where you have a scalar modifier and then a numerical answers in the question. And so one of the things I really always wanted to do is to work with real data. So not construct examples, but only take naturally occurring data and see what we can do with those. So the corpus is actually quite small. So I had 125 examples of those and only 20 of these. So it's a relatively small corpus. So then the next question was, if you have those dialogue, how do humans interpret this? So then I used Mechanical Turk to get answers to those questions. If you have, was it a good movie? It was a great movie. Do most people interpret this as a yes or as a no answer? And so I don't think I have to convince most of people here that Mechanical Turk is really like a very good way to get lots of data quite quickly. So that's what we used. We asked 30 Turkers, 30 judgments for every dialogue from different Turkers, and we asked them whether the answer of those dialogues conveyed a yes, probable yes, uncertain, probable no, no. Then in the end for the analysis I did collapse the probable and certain categories into one. So the probable yes and yes were collapsed into one yes category. But actually, I have all the data that I'm happy to share. So this is really like a great way to get very fast, answer, and also quite cheap. And also, what's quite important is a broad access, and access to a broad population. So here is, the kind of annotation that I got from Mechanical Turk. It is hurricane season extraordinary, very unusual in the sense of how many storms we've had. So is this reply meaning yes or no? And you can see that, most of the Turkers agree that it was yes. So then I computed entropy to have a notion of agreement or disagreement between the Turkers. So the closer to zero, the more agreement you have. Here there is another one where you see that there is more uncertainty carried in this kind of answers. Well, it's just one clip. Was it a good movie? It's an okay movie. Now, half people thought, okay, that means yes. Half people thought, it's only, no, it means no. So can we kind of, capture this kind of thing? So the first approach, so we have now this corpus and how humans are interpreting those answers. Can we automatically derive this? So the first approach I try to use is to exploit web data. So there is really now, like tons of data that we can get from the web, and it has been used a lot, especially to do, sentiment analysis, kind of weight word between positive or negative. But what I wanted to do is to do that, to do inferencing, and I'm going to show you that we can get somewhere. So to start with, I had really like a very simple model. What I did is to take the IMDb reviews, movie reviews. You have like scores from 1 to 10 that I actually centered around 0. So the more 10 is, like more positive review, and 1 is more negative review. And what I did is just look, at how often an adjective like great appears in the review, in the 1 category review, 2, 3, etc. And the hypothesis was that great would appear more often in the more positive reviews. So this is quite crude because it's only like kind of raw count of the appearance of that modifier in the reviews, and then you can kind of compute an average rating for that word. But it turns out that this is kind of giving us a reliable guide to modifier scale. So if I do this for disappointing, bad, awful, you see that this estimate score that I get is getting more and more negative. And this roughly fits with this idea that bad is more negative than disappointing, and awful is even more negative than bad. So you do get this kind of ordering that I was looking at modeling. Same here on this side for the positive adjective, enjoyable, even better, great, even better, superb. And so I could use those scores to do inferencing. So the way I did that is that if we have scores that differ in sign, you answer no. And if you have the absolute value of the question or word that's smaller than the absolute value of the answer word, then you can say that yes, So this is how I try to model those dialogue where I had both a modifier scale in the question and in the answer. So then how did I do this for the numerical example, the few numerical examples that I had in that corpus? I queried the web to find, positive example and negative example of what counts as little kids, given the numerical measure that you have in the answer. Here. And so you can get, some snippets from which you can easily extract the age, and then you get, this bunch of negative example, positive example, and you can fit a logistic regression to get the probability by age of whether little kids of that age counts really as little or not. And then, use this probability that you get to try to classify your example. So here are the results. So for the modifier one, we get 60%, And then for the numerical one, so recall that I had really few examples here. When you can do a model, when you get enough data to build this logistic regression model, it's very precise. The probability that we get from the web was really fitting with human judgment, but often we have a very poor recall because often I didn't find enough data to be able to, negative example, to be able to fit this logistic regression. So we'll come back to that in a minute. But so here were, graph that I got for young kids and the age or warm weather and the degree. And that would really fit well with human intuition. Though again, here we don't really take context into account. And so this is just like, a global idea of whether weather is considered warm or not. And of course, this is like very crude, right? Because probably a warm weather in Baltimore is not the same as a warm weather in Florida. And so the problem of low recall was really an important one. So often I was not able to find enough data. So I had questions like this: do you happen to be working for a large firm? It's about 350 people, where there you hope to get an idea of whether 350 people does count as large or not. But the problem is that when you try to query the web for that large firm and then people, instead of getting number, I would get a lot of snippets talking about the personality of your colleagues. So whether you were working with not nice people or very nice people, but they were really not picking up of this idea of size of the firm. So then, there is nothing you can do about that. Then looking more at, exactly the kind of data that we get, one of the things that was quite nice is that you do capture canonical antonyms, like was it right, it was wrong, and then, that's good that we can capture that. But what's more interesting is that we can capture this kind of contingent opposition. And so here are some examples that you would not find as antonym going through the graph in WordNet, for example, or in some thesaurus resources. So are you still optimistic when you look at it that way? So here the context that I omitted on the slide is they are talking about the seawall, and there is like heavy water coming, and they wonder whether it's going to go on top of the seawall. Answer: we are very, very worried about the topping of the seawall. And so this model is really able to see that here we have like totally opposite terms. And this one is a bit more interesting. Are Republicans confident that in this election year the president can help them prevail? Republicans are nervous. And so here those are not really canonical opposites, confident and nervous, but in this context they are really like, they should be seen as opposite. And even though our model didn't really have, any context, it did find an opposition here. And so, of course, going back to this idea of there is like inherent uncertainty in language, what you want to do is to get a model that would be highly accurate when most people do agree with each other. Yeah.
So I'm just wondering, so the example that you gave that you were learning from the reviews was things like, good and bad and awful. And
yes.
are clearly things that people talk about in the reviews. But
no, you do find, yeah.
So people do actually use it.
Yeah.
It's surprising to me because it's not.
So that was surprising to me too. Yeah. That actually most of the work that I had found, and there, probably it was on the slide, but I forgot to say that those dialogues came from the Switchboard Dialogue Act Corpus and from CNN shows, where you could think that this is totally remote from movie reviews. But then it's really surprising to see the kind of words that are actually used in those reviews, and that you do get something that confident here is much more positive than nervous. That's what the model would learn. And I mean, I can give you, those counts that I got out of this IMDb corpus. Yeah, so this, I was kind of really surprised how well this kind of crude method looking at just, movie review actually, go back. Yeah, good point. I should have explained that better. Does that answer your question? So then what I wanted to have, we want to have a system that's going to be highly correct when most people agree whether it should be a yes or a no. And so this is what this graph is trying to show. I plotted here the entropy of the response distribution. So the closer to 0, the more agreement you have. And here it's the data points that the system got incorrectly, and above the data point that the system got correctly. I jittered them vertically, otherwise you would not be able to see them. And what you want is that you want a lot of data points in that corner, correct and highly confident. And so it doesn't really, what you also don't want is too many points here that the system would not get correctly, but most people did agree whether it was a yes or a no. And it's roughly doing a right job. So here what I try to do is to really show that, crowdsourcing techniques that have been, now used a lot in NLP for, machine translation and stuff like that can also be efficiently used to tap into readers' intuition. And I think actually it's extremely well suited to do that because, as I said, you have a broad access to population and you can just ask them judgment that they do every day in using language. And then also we can ground meaning from unstructured data, and we can so build model of word meaning that can be used in many other contexts than only doing sentiment analysis. You can really do human reasoning with those. And then we can kind of deal with this pragmatic interpretation. So then next, I jumped on the neural network bandwagon recently, and we were quite intrigued. This is work I did with Jo Kyung Kim, CSC student at OSU. We were intrigued by this Mikolov et al. Paper, where they try to show that in those neural network model representation, you have a lot of syntactic and semantic regularity. So perhaps you've already seen this graph where they show that you can have like a gender transformation. What's the vector that's map, the vector representation for man to woman? If you apply this to the representation for uncle, you would get to aunt. If you do this for king, you would get to queen. And so their message there was trying to say, like, all those representations that we get from those networks are actually interpretable. And so I thought that this was something that we should investigate a bit further. So they also had like this number transformation. You can go from king to kings, the plural, and so then if you can also kind of combine those transformations. So if you combine the gender transformation with the plural transformation to the word king, you would get queens, so the plural of the feminine. So then the question we had is, can we use those representations to find the scales that I'm interested in? And so what we did is just use the off-the-shelf continuous word representation made available by Mikolov et al. On their website, and try to see whether we could get the scale out of these. So here is the architecture from which they derive their representation, and I'm not going to go into details. The only thing to point out is that we used the highest dimension of the vectors that they provide, 1,600 dimension, and because there is some recurrence here, those representations are really capturing some context. So the word sequence, it's not a bag of word model only. The sequence of the word in the text does matter. How did we use those? So we had this hypothesis that if we have like two opposite terms, like furious and calm, those representations along the line here, if you take intermediate point, we would have some word that would go from furious, a meaning of furious, towards a meaning of calm. And so first, to just investigate that, we just look at taking the first quarter, half, and third quarter, and see what would be the closest word in that continuous space that we get here. And here you would get angry, so closest in cosine distance. Angry, tense, quiet, and calm. And so looking at this, we thought like, yeah, we do get this scale from, like angry is less than furious, tense is even less than angry, and then, you get to calm. So let's just, qualitatively evaluate this. Here are some scale that we got exactly the same way as I just showed. So the first one is the one I showed you. Here, if you take furious and happy, and you go along, you get angry and happy, pleased, which seems reasonable. Terrible, horrible, incredible, wonderful, terrific, cold, mild, warm, sticky, hot, so seems to be quite good. Ugly, nasty, wacky, lovely, gorgeous. So looking at this, we thought that there is probably something in that idea that the representation that we get from those networks are really interpretable. So just like another test that we did is, let's assume you take the base form of an adjective and the superlative. What should be in the middle? Then probably something close to the comparative. And so if you look at this, so you get good and best, and you look at the closest word in the middle. Here you would get better, here you would get slower, and there you get faster. So it does work, and I didn't cherry pick those examples, right? But of course, there is always a lot of noise, and so here bad and worst, you get terrible, but not that far from the middle, you get something like great, right? Which is not super. But still, we thought that maybe using the scale that you get from those representation, we can answer the indirect, we can infer yes, no for those indirect answers to the question. So how did we do that? So if we have something like, is Obama qualified? I think he's young. You take the antonym of the question word, unqualified, and then we assume just arbitrarily that we would look at the decision boundary to be the midpoint. And we see where the answers words fall with respect of those two words and the decision boundary. And if it falls on this side, we would answer no to the question. If it falls on the other side, we would answer yes to the question. And I think that's actually modeling quite well how scalar implicature do work. Because if you have words that are really similar in meaning, people tend to then go with a yes answer. So what's crucial here is actually to choose the right antonym from WordNet. So was the movie good? It was excellent. What are antonyms for good? Because we don't do any word sense disambiguation, okay? So we can look at the different antonyms that we get from WordNet. You get like bad or evil, but you have to choose the right one. And so what we assume is that we would just take the most collinear one between the question word and the answer word, and so here we would go with bad. So just to compare, so Motarami et al. Also used that corpus that I had created, but they use SVD instead of those neural network representation, and so in their model here, this is really a bag of words model, but otherwise the technique is roughly similar to the one we used. And so here are the results. So the first line is this IMDb model that I just talked previously about with an accuracy of 60%. This new model gets a much higher accuracy, statistically significant. And then to compare with Motarami et al., I use their measure, which is actually the macro average precision and recall for yes and no answer in the data set. Not convinced this is the best way to evaluate this, but the only way I could, kind of compare is to report, my number in their same measure. So in their paper, they actually also report higher results, but with a model that, when you think about it, is not at all learning scale. So I don't think this is suitable. I mean, here what you really want to do is to infer answers that how do you cognitively, come about those answers is because we know the scale of, good and excellent. So we want to have a model that does model this and apply it. And so just to show you a few examples here, do you think she'd be happy with this book? I think she would be delighted by it. So you have happy, you take the antonym here, and then you draw the boundary and check the side of the answer word. So delighted, and so here you would say yes, and this is, fitting with the turquoise intuition. Another one, do you think that's a good idea? It's a terrible idea. So again, you take the antonyms, you put the decision boundary, and you see where the word falls. So here it would be no. The president is promising support for Americans who have suffered from this hurricane. Are you confident? you are going to be getting that. I'm not so sure about my insurance company. So again, you take the antonym and you look where this word fall with respect to that decimal boundary. So something I mentioned to say is that if you actually have an answer that's negated, the way we would do this inference process is just reverse. We would do if everything was, not negated, and then you reverse the answer that you get. And in my corpus, I had just manually annotated the negation, but then, of course, using the Stanford dependencies, I tried to see whether I can automatically derive negation. And yeah, sure enough, going through the Stanford dependency graph, you can get a negation almost, 100%. One of the examples I didn't get automatically was something like we had a view of it, but not a particularly good one, because there the negation of you have to see like there is a problem of correct there that the system was not doing at all. So then again, what I want to do is we want to have a system that does well when everybody is agreeing. So I kind of did the same graph as before, and it's exactly the same picture, that you get a lot of good answer, of correct answer by the system when people are highly confident about it. And not too many errors when a lot of people were also agreeing with each other. And then again, checking for this kind of contingent opposition, we do learn those two, actually different one, but so maybe there is a way to combine those two models, but we get stuff like, is Obama qualified? I think he's young. Would that be acceptable? It wouldn't be unprecedented. 2 people are dead. Is that right? That's unconfirmed. So then also recently the Melo and Basal also tried to learn scales, adjectival scales, and how did they do that? They looked at linguistic patterns that have been proposed in the linguistic literature for identifying those gradable adjectives, and not only identifying those gradable adjectives, but seeing what's the order of the scale. So it's excellent, stronger than good, or vice versa. So if you have something like good but not great, you would infer that good is weaker than great. So they try to find, data on the web using those patterns that I put here, copy-pasting their table from their paper. And then when they used a method from Basal to kind of look at frequency and get a score for those patterns. And then when they have all of those, you can kind of enforce some constraint and use ILP. If you know that good is weaker than great, but you also know that good is weaker than excellent, you can get that excellent is weak. What did they say? That you see how this can work, right? You can kind of enforce some constraint there. And they released a data set that has this form. So they had much more data than me. So 569 pairs clustered in 88 entities. Where you see here how to read this is that you go from known, famous, legendary. This is more and more strong, close, near, intimate, nearby, close, adjacent. And here they kind of put the seeds they started with to kind of get to those words using WordNet. And one of the measures they report is pairwise accuracy. So do you get the right ordering for every pair? So then I compared the RNN representation with their model. So here, let me walk you through this table. So that's the inter-annotator agreement that I report for that data set that I just showed you. So 78%. I guess that here they could have also then taken a subset of the data where everybody agreed to have a really kind of a gold standard data. And then here what I briefly outlined is those results here, 69.6, but then they also add further constraint to their ILP using synonym information that people, when they went through this annotation here, marked. Okay, so here if you have some information about what counts as synonym, of course you can boost the result. So let's then look at the result of the RNN representation. If we try to look at all the pairs, those 569 pairs. Of course, all the words are not present in the Mikolov et al. Representation. But let's be harsh and assume that we don't get any of those right. Okay, so this is very harsh, right? What we get is 62%. Probably what we could have done is then for the one that we don't get, let's do a random guess, and it would be higher. And then if we just focus on the pairs that are present in the representation, those vector representation from Mikolov et al., which actually is 80% of the data set, so quite a lot. And we use the method I outlined before with the word-net antonyms, we get 71.8%. And if we use the given antonyms, so the one that are present in this data set here, and we get a slight boost to 75.2%. But so the point here was just to have like another way of evaluating the quality of the skills that we get from those RNN representation, and I think it's kind of quite good. So here what we did is to give further evidence that the representation that we can get from those continuous vector space are actually really interpretable, and so that there is probably something there. And so we did actually successfully learn the scales, as we've shown as the high improvement over this IMDb model, and also on this DeMello and Vansal corpora. So what I wanted to do next is also to look at a bigram. So often in dialogue you don't have just an adjective, but you have a modifier to the adjectives. You say stuff like, so good, quite good, really good, and can we then, get the meaning of this? And so just, for the fun of it, probably you've already seen this translation phrase explaining, how British say stuff, what foreigners interpret, but what do the British really mean. So if you have something like quite good, I guess everybody thinks it means quite good, but the British apparently means something like a bit disappointing, very interesting, they are impressed, this is clearly nonsense, I almost agree. So you see again like this kind of adverb to a verb here is not far from agreement. I don't agree at all. But I mean, aside from the joke, what I really want to do, if I have something like very interesting, can we get to the meaning compared to quite good? How does that scale with excellent, for example? Can we kind of also have like much more sophisticated scale rather than just like raw adjectives? And so I also wanted to just tell you a little bit about a project that really just started now with a student in BMI and CSC at OSU, looking at how are gradable adjectives used in clinical notes. And so this is really something we started, and I welcome any feedback of how we could go about this. So one of the big thing they try to achieve in BMI is try to automate the process of seeing whether a patient does fit a trial. So you have like a lot of criteria for being able to participate in clinical trials, and they take a lot of time, and humans do that. They go through clinical notes and try to see whether a patient does fit this trial or not. And so you have both like inclusion and exclusion criteria. So let's look here at some criteria. Patient with severe cardiac disease, diagnosis of aggressive lymphoma, major surgery within 3 weeks, mild pulmonary symptoms, patient with stable CLL disease. And what does those mean? What counts as like a mild pulmonary symptoms? Can we automatically do this? If we could automatically do this, then it would really help the process of those annotators and clinical trial coordinators. And they actually report that when they have criteria with those kind of gradable adjectives, it's really hard for them to know what to do with this. And so one of the things, for example, just to give you an idea of what's going on there, so you have like this concept of ejection fraction, that's the percentage of blood that gets ejected from your heart each time the heart pumps. so this is like a numerical value, right? You can kind of really, you can have like a test and get a numerical value of what's the ejection fraction for you. And they talk about this as, if you look at the clinical note, they talk about this as hyperdynamic, normal, low normal, borderline, mild, moderate, severe. And you would think that there would be a range of values associated with that. But apparently, from interviews with doctors over there, the only thing they report is that that normal is 65. And they are aware that there is a range, but they cannot tell you the range. So of course, as computational people, we can get that. Okay, you can look at the data and see that they talk about borderline when it's 43, severe when it's 20%, and so you can kind of give some guidelines there. And if you look at heart failure trials, actually like half of them do mention ejection fraction, and in 5% of them they don't really indicate a precise numerical value, which you think they would, right? But and then they just say like you want people with a severe ejection fraction. Okay, but so I mean, what does that mean? Who counts as severe and who doesn't count as severe? But so we can just get data from those clinical notes, right, where we have the ejection fraction and then just, like the posterior probability using Bayes' rule of when is something, when is an ejection fraction qualified as normal, borderline, hyperdynamic, etc. And so you see that we didn't have a lot of data for borderline. So this was one example, but they have like other concepts like that are tied with numerical values, and maybe if we can already automatically do that, that would help them to already assess eligibility or not. But the thing that interests me more is to try to get at what does it mean to have a mild pulmonary symptom. So here are examples that have been the doctor report as positive example or negative example. Like her shortness of breath remains stable, but she's able to walk about a block daily. That counts as a mild pulmonary symptom. Patient reports ongoing non-productive AM cough. That's also positive. He reports nocturnal dyspnea and thinks that his chest pain has become more pronounced in the last 3 days, positive. The negative here, he was unable to speak full sentences. This actually is not mild, but it counts as severe. Okay. When you ask them, what is this? They would say, this should be a severe symptoms. Here, this one, you have nothing, right? It has no anxiety, no breathlessness, no insomnia. It's not mild, it's not severe. I mean, it's not a symptom anyway. And here, I mean, to show you how tricky this can be, his chest pain is likely due to use of cocaine. So even though in this case, that chest pain that was also associated with dyspnea would count as a mild pulmonary symptom, here chest pain that's actually tied to cocaine is not then a mild pulmonary symptoms. So what we started doing there, so Chaitanya, she developed a web-based application where we asked annotator, so doctors, nursing students, to go through a clinical note having in mind a criteria and then decide whether reading that note they would say, so what people actually do, right? That's how they do to kind of decide whether someone fits a criteria or not. Do you think this patient fit the criteria? So a global assessment, and then what in the text makes you think that it does fit the criteria or not. So here it's how it looks like. So they have this global assessment, definitely yes, probably yes, maybe, probably no, definitely no. And then they can highlight, what in the text makes them think that it does fit aggressive leukemia. Of course, sometimes, a note is not relevant and they can just skip it. But so since, we've been also working, recognizing textual entailment, then we were thinking with Chaitanya, maybe this is kind of another way of viewing textual entailment. So for people not familiar with textual entailment, what a system is asked to do there is that you would get a passage and then a hypothesis, often shorter than the passage, and you would be asked, if you know that the passage is true, would you entail the hypothesis? So something like, Obama is visiting Europe, Obama is traveling, if you take as granted that Obama is visiting Europe, then you would say, yes, Obama is traveling, right? And so maybe we can do this differently and think like, does a clinical note actually entail the eligibility criterion? And so view this kind of thing as kind of a training data for this new textual entailment task, and have like those passages being like positive example of entailment of the criterion, and those would be like not entailed, with actually this one being the an entailment one for the severe criteria. But so this is really like a project that we started doing, and yeah, welcome any feedback that we would have about, you know, where we should go with this, or, you know, whether we should do this differently. And so before ending, I just wanted to advertise a bit NLP at OSU, if that's okay, because now we have a lot of people over there, and maybe you don't realize that, and if you have good undergrads that would like to do NLP, and perhaps in the linguistics department, if they have, you know, also like core interest for, you know, syntax, prosody, child language acquisition, we have like also a lot of good linguists at OSU. But so here on the slide, I only put the people that are really computational linguists in linguistics. So we have Mike White in natural generation. We have William Schooler, more like cognitive modeling. Micha Elsner, who also joined OSU last September. So me, I joined in January. And then over in CSC, we have Eric Foster-Lucier more in speech, and then Alan Ritter is actually joining CSC this coming September. So I mean, he knows a lot about social media, of course. And then in BMI, we are working with Albert Lai. So yeah, just, you know, if you have students that would like to do a PhD, maybe they can also have a OSU in their radar. But yeah, I'm welcoming question if you have some.
I have no intuition on why neural models are learning gradable. So a lot of this distributional work, you would say that, you know, these things tend to modify this class of nouns, or these things modify this other class of nouns. So I could see how you learn this, how these neural models would work if you were training purely on product reviews, but that wasn't all coming from the ones that you downloaded. Those aren't coming from reviews, are they? It's from general data.
The dialogues that
No, the ones that you're basing on the
word representations that you downloaded from Nickel. What corpus were those trained on?
yeah, no, they are not from product reviews. Yeah,
right, they're not coming from product reviews. So then, so I'm just having a hard time thinking. Like, do I normally say lots of bad things about dogs and good things about cats, and there's something in between that's?
Yeah, so this is really also what kind of started this work. Is that, I mean, now a lot of people are using those, you know, representation. And when I've seen that paper from Nicolas, we were like, okay, maybe there is. I cannot explain to you how this is happening, right? But it seems that there is kind of some clearly semantic relationship that is coming out from those representations. How they are coming out, I have no idea.
I just can't see what the textual correlates would be that would drive that mistake.
You could say like cats but not dogs.
Yeah, so I mean, the examples that those authors use of king to queen and gender and things, and that's going to be very, very hard properties that these tend to be subjects or objects of these particular verbs, or certain adjectives apply to them, and when you subtract out certain feature vectors, you get subsets of these, and that all makes very intuitive sense on how you get that from text. But the scalars, it would, I mean, if you directly map the same intuition over, it would have to mean that there are some classes of words that you tend to be very negative about, and then some class of words that you tend to be positive about, and something in between that you're sometimes positive, sometimes negative. And I just don't have intuition on where they would.
So the way we started looking at that was, we actually started with which came later in my talk, with this base and superlative form, where for some reason in my mind I had the impression that that was roughly similar to this like singular plural, where you can think like, okay, I can kind of have this transformation between, you know, like singular plural, feminine and masculine. If you kind of assume this linearity assumption there between like a base form and a superlative form, and there would really be a relationship there. What should be in the middle? It should be the comparative, right? If the heuristic, this intuition is correct, right? And it seems to be happening, right?
You know, I really like your examples. These experiments really do show that. And then well, where is that coming from? And I think because that result is more intriguing to me than any of the previous results. Just king, queens, ants.
I have to say
That's pretty easy to do. I mean, this doesn't seem like it should. I would have thought that it shouldn't happen. Like if you had told me you were doing this, I would have thought this isn't going to work.
I was actually very skeptical, you know. I was skeptical too. But even the singular plural, I was like, okay, I mean, is there something more, right? I mean, is that it? That's there? We can find something else. Actually, something else we also looked at, but it doesn't make sense to me. So you know, I never included it. But I mean, I can tell you, we tried the kind of the infinitive form of a verb. So of course in English, you know, it's like infinitive or plural, right? Need, for example, and the past tense. And what you get in the middle is the term present. Needs. And this is, I tried a lot of work, and systematically you get that. Or systematically, I'm exaggerating. But then, I mean, I have no intuition. What's the link there between like an infinitive form or a plural form, and you know, like the past tense of a verb and the middle. I can show you the example if you want. But so I think there is something to explore in those representations that we are getting from the neural network. And I mean, frankly, when we did this, is we just took their representation of the shell. Right? So I thought that was also like a nice exercise to take something that's out there and what can you do with it. Yes.
So that's sort of like a comment / question, and then another question. So first comment / question is, so I've read work that someone did on something similar to this, where they basically did a bunch of web queries, collected the snippets, and they did like a pattern. So they would sort of pull out the actual gradable adjectives they were interested in, just look at like a template. And then they would go through and they say, okay, given two query adjectives, how can I fit them into templates? And which ordering of the adjectives are more frequent in that particular template? If I know what that template implies, then I can make that difference. Do you think, or to me, it kind of seems like what these RNN embeddings are doing is sort of like automatically finding templates, right? Because don't they sort of look at an arrangement of words and try to update the vector representation based on sort of what things are next to it in that sentence and everything? I have no idea how they really work, but it seems like what they're doing is they're looking at small contexts like that, so maybe it's sort of picking up automatically.
So that would be an answer to a Benjamin's question.
Yeah, so anyway, that was interesting. But then the other question I had is, did you look at if you look at colors or things that aren't gradable adjectives in the vector representation, did you play around with that and sort of see?
I didn't look at that. Yeah. See whether you would like pink, red. Is that what you're?
Yeah, no, I just know that there's. I worked on adjectives for a little while, and there's this there are all these other classes that we don't really know how to deal with. So like in WordNet, I was working on WordNet, and we knew how to deal with. We had a way of dealing with scalar adjectives, but when it came to like colors, it's really difficult to understand what's a nice formal way to represent relationships of colors. So I wonder if these vector space representations can maybe see.
I see. Yeah. I never looked at it. But you can do it.
Yeah.
You download me for help and then you see what's going on. Yeah, interesting actually. Yeah, it would be good. But yeah, I think it's worthwhile exploring a bit more, those representations that we, because I think there is kind of a bit of a mystery of, what are those vector representations. The question. Yes.
Can you go back to the multimedia example, the Siri example, to just give a little bit more explanation of how this can help this kind of question?
Where do you want me to go back?
I was trying to reconnect what you said in the talk back to the first few pages. For the love of God, camera is on, please help me.
Next.
No, so what I'm trying to say is that so here when you hear this from a lot of God, the cameras are on, give me something, you get much more than only the literal meaning there. There is like a lot of information that you get to understand why is Stephen Colbert uttering here and what would he want, right? And that's the same when you have those kind of indirect answers to question. You have like, it was good, it was excellent. There is much more information. You know this kind of scale of adjectives. That excellent because of experience, exposure to language. This is something that you kind of learn. And when you get that answer, well, it was excellent. Then you kind of really connect that to good immediately, and you know that what it means is that like yes, it was good, even better, right? Because you have that representation of the scales in mind. So that, yeah, I just wanted, but that was just like more to kind of show you, we are far from having machine being able to do this. But when you hear this, you don't think a second, right? And you immediately understand what this means, right? And you need to do a lot of reasoning actually to get to what this means. And it's because of the context and a lot of things that we are not able to model right now. Yes?
I have a clarification about whether Obama is qualified.
Is Obama qualified? I think he's young.
Right. So I think you mentioned when you're using recurring networks that it is taking into account some of the context of the sentence. So if that instead of Obama, the question was if Obama was qualified was like a sportsman.
Yeah.
Young is probably the same. Could be qualified. Would that be a positive thing?
Yeah, so the thing is that we are getting what I mean is that the representation that we get, so they learn a representation for qualified, that is dependent on the context in which qualified appeared in. But I have no idea, I didn't look at the training data for those RNN models, so I didn't train the RNN myself, right? So it's not that in those examples I'm not taking Obama and everything, but yeah, context is definitely this is like the first step. But I agree with you that context might make a difference between how people do interpret qualified and young in what you say. But so kind of here, like if you ask people is Obama qualified, I think he's young. What most people would then get is that no, that's not good. And this is kind of what you also get from those representations. Train on something totally different. But I agree. Yeah.
I think it's here.